So let's try this in another situation. Here are two domes at Mount Stromlo Observatory. One on the right and the one on the left are two different domes, but they have apparently the same angular size, so we might think they're the same distance. But far more is going on here than meets the eye at first. As we zoom out, we see that the two telescopes are intrinsically very different size. We judge their size relative to Paul Francis, you will see that one is very small and the other very, very large. And the same problem happens when we look at galaxies. This small galaxy you would think would be much further away than this large galaxy because the angular size of the small galaxy is so much smaller than the large galaxy. But these galaxies all reside in the Virgo cluster, and they are all the same distance, about 40 million light years away. So let's look at another way to measure distance. The universe is literally full of stars. Our sun is a star. But the Milky Way is made up of millions upon millions of suns. And then there are other galaxies, just like our Milky Way, made up of billions of stars. And then we look far enough away, there are literally billions upon billions of galaxies. If we can use how bright objects appear to measure the distance, then we would have something we could use all over the universe. Now let's come back down to Earth, to Canberra, in fact, where we look down Anzac Parade. And what do we see? Well, we see a kangaroo, but we also see a bunch of lights. And these lights are at further and further distances from the camera. So one can imagine in this image measuring how bright these lights appear as a function of distance. Now this image is taken with a modern digital camera, and it records light in three colors: red, green, blue. Now we want to only use one of the colors to measure the intensity of the lights. So we're going to use the green image. So here is the green image of that picture of Anzac Parade. And we see the lights here represented in black and white. The whiter the picture is, the more intensity that represents. All right, so let's zoom in to part of the image here. So if we look at one of these lights up close, we see that the light is a series of pixels, each that have different intensities. And so when we are going to go through and add up how much light there is, we're really going to add up all those intensities of each part of the light and count it. Now we can do that for each light and compare it to the distance measured from a satellite image. This is shown in the next plot. So here's the result of our experiment. That nearby light had a lot of intensity. That intensity is how bright the pixels were, and those represent how photons interact with the detector. When a photon hits a digital detector, it creates an electron, and the electronics count that electron. So this one has 50,000 electrons detected. When we go to a more distant light, then we see that the object's further away, but we measure fewer electrons on the detector, which means fewer photons were collected by the camera. And as we go further and further away, we see a pattern that the further away we are, the fainter the object appears in its measured flux. So let's look at the physics of what's really happening. Imagine I have a light bulb, and this light bulb is putting out energy per second. We call that the luminosity. And the luminosity is typically measured in watts, which is energy per unit second. So the energy of a light bulb might be 10 to the 2 watts or 100 watts. And the energy of the sun, for example, is much larger. It's about 4 times 10 to the 26 watts, which is a very big light bulb indeed. Now, as the light of the light bulb goes out, it's spread out into a sphere. And so if you imagine that I'm a distance, for example, r from the sphere or from the light bulb, and I have a telescope that's going to look at that and collect all the light, put it onto a detector, count how much light there is there, how much energy it receives, and that telescope has area A, then you could imagine that the total energy per second received by the telescope is going to equal to the luminosity of the light bulb times the fraction of the area of the sphere the telescope represents. And that's going to be its area divided by the surface area of the sphere, which is 4 pi r squared. Now, to make life a little more complicated, we know that telescopes come in all different sizes. Our eye is a telescope, so our eye has an area of about 1 centimeter squared, or that's about 10 to the minus 4 meters squared. The Keck telescopes, which are among the largest on Earth, have collecting areas of about 78.5 meters squared. So to get around the fact that we have different sized telescopes, astronomers come up with something known as flux. So flux is energy per unit area. So the flux of an object, if I want to know its energy per unit area, is then the luminosity of the light bulb divided by the area that the light is spread out of, and that's just the surface area, so 4 pi r squared. And you will note that both the energy or the flux are both proportional to 1 over r squared. So we expect the energy detected on a detector, like a camera, will be proportional to 1 over r squared. The exact amount of energy depends a lot on how big the telescope is and how, for example, efficient the detector is at converting light into things that it counts and thinks is light. But those details don't really matter if you use the same telescope or camera. And that's the case, of course, that we have in our picture of Anzac Parade. So let's see how well this 1 over r squared prediction fits our data. So here's that 1 over r squared curve plotted over the data that we collected on Anzac Parade. And you can see that while the curve does not perfectly fit the data, it seems reasonably to explain what's going on. The reason it doesn't fit the data perfectly is because there's uncertainty, both in how far away the objects are and how we measure them, but probably more to how we measure how bright the objects, the lights appear on the detector. That turns out to be quite a challenging thing to do given the shape of the light bulbs. But we can use this whole process in a very analogous way to measure the distances to stars or even galaxies of stars. All we have to know is that we have something that's more or less the same brightness.